Okay, welcome to lesson 3. I want us to look at how we can now use colligative properties to calculate relative molecular mass. So I'm saying here now, calculation of relative molecular mass of calculation of relative molecular mass of non-volatile solutes. Now, what is now clear is that the depression in freezing point, is directly proportional to the number of moles of the solute. Okay? Depression in freezing point is directly proportional to the number of moles of the solute, of the non-volatile solute that you have dissolved there. Meaning that the more the number of moles of the solute particles, the bigger the depression in the freezing point. So where N is equal to number of moles of non-volatile solute particles. Okay? Now, but all of us know, but N is mass over molecular mass, meaning that we can say that dT F is directly proportional to mass, but inversely proportional to molecular mass. If we introduce a constant, then that constant should actually be Kf, mass over molecular mass. Now, this formula here is given in many books, but is not used to calculate molecular mass. We normally want answers from first principles. So this one here, we can see that where dTF is the depression in freezing point. Okay? Kf is what we call the cryoscopic constant. And then M is the mass of non-volatile solute. And then Mr is molar mass. So, yes, this formula and this expression here are normally given in some books, but calculations from them are not really valid. We want calculations from first principles. But we can use that formula to show that, yeah, there is a relationship between molecular mass and depression in freezing point. As you can see, that dt is inversely proportional to molecular mass, meaning the higher the depression in freezing point that you get, the lower the molecular mass that you have. So let's see some examples here and the way we work from first principles. So example 1 here. Example. So in the example I have here, it's saying a solution containing 4.5 grams of a solute B. A solution containing 4.5 grams of solute B in 125 of water, in 125 grams of water, freezes at negative 0.372 degrees Celsius. Determine the relative molecular mass. Determine the relative molecular mass. This is what we are calling RMM of B, relative molecular mass of B, if the cryoscopic constant of water, if the cryoscopic constant of water is 1.86 degrees Celsius per mole per kilogram. Per mole per kilogram. So we have a question like that. It's giving us a lot of information, and we are supposed to use that information to calculate the relative molecular mass of that non-volatile solute B, using first principles. Now, the first thing that we need to do is to find out, do we have dt in that equation? Do we have the depression in freezing point? Remember, depression in freezing point, so I'm writing here solution. You say dt F, depression in freezing point, should be the freezing point of the solvent minus freezing point of the solution. So let's see what the question is giving. They are saying a solution containing 4.5 grams of solute B in 125 grams of water freezes at this temperature. So what is this temperature? This temperature is the freezing point of the solution. And when you read, they don't mention of any other freezing point. But at least we know the solvent. So in this question, the examiner was taking an assumption that you know the freezing point of water. So freezing point of water should be well known to us. So remember, we said T naught is freezing point of the solvent because it is always higher, and T is the freezing point of the solution. In the question, there is the freezing point of the solution. So we can now say that freezing point of the solvent, water, the solvent freezing point is 0. So 0 minus freezing point of the solution, which is minus 0.372. And that is a positive answer, which is 0.372 degrees Celsius. That is our dt. So we have this dt. This dt of freezing point depression is caused when 4.5 grams of solute B is dissolved in 125 grams of water. Okay? But then in the question there is a constant, what we call the cryoscopic constant. Cryoscopic constant, we said, is depression in freezing point. It's also dt. So depression in freezing point that occurs when 1 mole. Now 1 mole weighs a mass equal to relative molecular mass. So this constant helps us to relate to molecular mass. But this constant here is for 1 mole that dissolved in a kilogram of water. Yet here our mass is dissolved in 125 grams of water. So it would be very hard for us to relate this depression caused by this mass in this amount of water to this depression which is for 1 mole in 1,000 grams of water. So what we do is to change this mass into 1,000 grams of water. we create an assumption or a relationship that if 4.5 is in 125, what about, or what would be the mass in 1,000 grams? Such that we can now relate these dt, because these are dt's, but one is in kilograms of the solvent, this one is in 125. So for us to be able to relate these two, we must also change the masses to 1,000. So by first principle, you will say that 125 grams of water dissolves 4.5 grams of solute B. Okay? So what about 1,000? Will dissolve. So you create a relationship. This times that over this. If we want to get that mass, so you say is equal to 4.5 times 1,000 grams over 125. And we get the mass of B that will be in 1,000 grams. Why am I converting it to 1,000 grams? Because my constant was given in 1,000 grams, which is 1 kilogram. Without changing, then I couldn't be able to relate them. So I would say 4.5 times 1,000 divided by 125. I get 36 grams. So 36 grams of the solute will now be dissolved in 1,000 grams of water to cause this depression. So I've been able to change or to fit the solute from 125 to 1,000 grams of water, because this one is also in 1,000. I now have the ability to relate. I have now the ability to relate the constants also. Okay? Why I'm going to relate the constant? Because I want to get the mass in 1 mole. So I can now say that this 0.372 degrees Celsius is depression caused by 36 grams of solute B when dissolved in 1,000 grams of water. So now 1.86 degrees Celsius is going to cause for 1 mole. And 1 mole weighs a mass equal to relative molecular mass. So I would now say 1.86 degrees Celsius is depression caused by 1 mole, which is molecular mass, and will equal to, remember, is now also dissolved in 1,000. This one is also in 1,000. So there is uniformity in solvents there. So which is equal to, so I make this relationship, this times that over that. So I say this is now 36 times 1.86 over 0.372. And that is, so I get my calculator, and I'll say this is 36 times 1.86 divided by 0.372. I get my molecular mass here as 180. This can be grams if they are not saying relative molecular mass. So you realize that we are able to determine the molecular mass by first principles of a solute that is non-volatile using colligative properties. So this now can be added onto methods of determining molecular mass when you want to determine the molecular formula of a compound. I can give another example here. That example 2. Example 2. Example 2. Example 2. The cryoscopic constant of benzene is 5.12. They are saying the cryoscopic constant of benzene is 5.12 degrees Celsius per mole per kilogram. Full stop. And they are saying a solution, explain the meaning of the statement. Explain the meaning of the statement. Explain the meaning of this. What does it mean to say that the cryoscopic constant of benzene is 5.12? Okay? What does that mean? Part B. A solution containing a solution containing 0.14 grams, 2 grams, 142 grams of naphthalene, in 20 grams of benzene, caused a lowering of freezing point, of 0.284 degrees Celsius. Calculate the relative molecular mass of naphthalene. Calculate the relative molecular mass of naphthalene. Full stop. So now, in lesson 4, we shall be answering this question together. The first part, very interesting. They are giving us a statement. Cryoscopic constant of benzene 5.12. Explain. What does that mean? And then in part B, we have a calculation that we shall be dealing with in lesson 4. I want to end here. We meet for lesson 4.